Calc students. Hope you guys have become acclimated and have your at-home learning space nice and organized and ready to go, because we are going to dive right into lessons, and I'm going to try to make this as clear-cut as possible. So please remember to watch my intro videos about contacting me and reaching out. I am certainly willing to Zoom chat with you if you'd like some additional kind of face-to-face instruction, but you just need to make sure that you speak up and let me know if you're having issues. So we are going to be in chapter 7. We are skipping chapter 6 for now and moving into applications of integration. So the good news, actually we'll start with the bad news. Bad news is you guys are the last of my 3 classes in terms of my prep. So I'm probably only going to have to make 1 or 2 instructional videos with my crappy cheapo stylus. So I just ordered on Amazon a nice expensive stylus that I can use to write on my screen. So hopefully that'll come in here in a few days, and so my handwriting will look a lot prettier. So there is my PSA. Please bear with me, and all right, I'll stop rambling. So the main concept of section 7.1 is how do we find the area of a region between 2 curves? Okay, so if you recall definite integration back from chapter 4, we discovered that if we have some sort of curve and we want to find the area under that curve, then we can go ahead and find that area by using an integral. So we can take the integral of, let's just call the function f of x dx, and we have to specify where from. So maybe we want to go from a to b. So that makes it the definite integral, and that would give us the area under the curve. Now, what do you think that we are going to do if we are trying to find the area of a region between 2 curves, this space right here? Well, we are going to take the same exact approach, but we're going to have to split it up into 2 separate problems and combine it back into one. So I'm going to go ahead and outline the approach that we would use. Is we need to turn to the techniques of definite integration, which you guys all showed mastery of. To calculate the area of a region bound by the upper curve. So in this case, this would be our upper curve. And then we would subtract sorry, I'm off my A game today. Subtract the area of a region bound by the lower curve. So this would be considered our lower curve in the diagram. So I really like the picture that your textbook put out for this problem. Okay, you can see this idea taking place. This is the same exact problem from above. Okay, but we're thinking about if we want to find the area of a region between 2 curves, then what we're going to have to do is we are going to have to look at that upper curve, I'm going to call it, and we're going to have to find the area under that upper curve. So what would we do? If we're calling the upper curve f, we would take the integral from a to b of f of x dx, and then we would subtract that from the integral of our lower curve area. So we are going to call that g of x dx, and again we have to go from specified points a to b. So if you notice, we are taking what I'm going to call kind of the whole section. We are subtracting the part that we don't want, and what is that going to leave us with? What our goal was the area of the shaded region. So when we think about properties of integrals, we know that subtracting 2 integrals can really be combined into one integral in and of itself. So we can represent that with a to b of f of x, that is our upper, minus g of x, that is our lower function, dx. Okay, and this right here is the key idea of the day. Okay, so now we are going to basically just summarize it into the formal theorem and then do practice problems. So the big concept is finding the area of a region bound by two curves. So first of all, we have to have two functions that are continuous on our interval, and we have to make sure, okay, this is true above if you go back and check, one function is always less than or equal to the other function. What does that mean? One function remains the upper function the entire interval, and one function remains the bottom function. Now they could meet and be the same, but you have to see that upper and lower idea. Then the area of the region that is bound in this situation by those two curves and the vertical lines that are drawn straight up from x equals a and x equals b is what we just wrote, okay? But just to make sure we all have it clear, area of the region bound by two curves from a to b is the difference between f of x minus g of x and then dx tacked on. Okay, now how can you kind of remember this? Informally, you can go ahead and write that we are going to take our upper function and we are going to subtract our lower function. Okay, now the cool thing about this technique, this approach, is that this method will work even if some of your function dips below the x-axis. And we're going to see that happen in some cases. But the subtraction along with negative numbers is going to make up for that. And that double negative will form addition, which will accumulate the area that we're trying to find. Okay, so like I said, now we're diving in to practice problems. So if at any time you feel like you're getting the hang of it and you want to put me on pause, try the problem, and then kind of speed me up and just see if you're correct, that might be a great learning technique from home. So the first example says to find the area of a region that is bound by the graphs of y equals x squared plus 2, y equals negative x, and then also we can see that our a and our b have been specified. When it's just x equals a number, that kind of gives you your limits of integration. Okay, so the first thing that you have to do is you have to graph this, whether it's on a graphing calculator or if it's on by hand. Okay, so let's go ahead and graph this first function, y equals x squared plus 2. Okay, so we have we're going to shift up 2, and then we have out 1, up 1, we have a parabola. Okay, and then what else do we have? We have negative x, so that's just linear. So we can go ahead and know that our slope is 1 and make your straight line. Sorry, again, the new stylus is coming soon. Okay, so we can clearly see that the red line is going to be considered what we said on the front was g of x because that's our lower function on the entire interval. And then we can go back and we can see that the green line is our f of x because it's our upper. Now you don't have to get caught up in remembering f and g means upper lower, but just kind of trying to make it all come full circle. So at this point, okay, this is going to be the same for all the problems we do today, but eventually it'll come up as something we need to really think about, is when we're looking at the area of the region bound by x equals 0 and x equals 1, okay, we're trying to figure out what this area is, and we are going to use those representative rectangles, which a lot of you guys wrote about in your extra credit, okay, because we are kind of taking that numerical approximation approach and turning it into something exact. So if we think about dividing that black area into super skinny rectangles, okay, what we're going to think about is the height of the rectangle is going to be determined by the function values, okay? This number, if we're thinking about a number line, is going to be f of x sub I. So x sub I is going to be something between x equals 0 and x equals 1. And then the bottom of the number line that we're looking at is going to be defined by the function g, and we're going to plug in that same x value, whatever it might be. So what are we going to do if we have a number, two numbers on a number line, and we want to know the distance between them? We are going to subtract. So the height of our representative rectangles, if we would envision dividing that area into millions of rectangles, would be defined by f minus g. And then the width, this kind of goes back to our limit approaches, is considered delta x. And again, the theory is you need to get delta x as small as you possibly can. So now the good news is we don't have to use limits because we know how to find the area under the curve. Okay, we are going to take the integral from 0 to 1. And what do we have to do? We have to take our upper function, which is x squared plus 2. And then we have to subtract our lower function, which is negative x. Be careful with those double negatives, dx. Okay, now this is a great review of integration. I know we've been away for a few weeks, so make sure you recall integrals versus derivatives. So now I'm going to first go ahead and just clean up my integral before I get ahead of myself. So I'm going to rewrite it as x squared plus x and then plus 2 dx. Now I can go ahead and integrate. So what is the integral of x squared? Using that power rule, we have 1/3 x cubed plus, power rule again, 1/2 x squared, and then plus 2x, and we don't write plus c because we have our upper and lower limits. Okay, so now let's go ahead and recall, what do we do with definite integration? Well, we have to input 1 for the entire function first. Okay, I'm not going to write this out for every problem, but it's been a while. Okay, and then minus, what are we going to get when we input 0 in for x on all three terms? We're going to get 0 because I'm running out of space. Okay, so from here we have 1/3 plus 1/2 plus 2. I'm just doing the cubing, the squaring, and the multiplication. And we have minus 0, so we can leave that alone or tack that at the end. And then finally, when we do the arithmetic there, we end up getting 17/6. So the area of that black region from the graph is 17/6 units squared. And you might want to put that label so you remember that we are finding area. Okay, so it would be a good idea now to pause me and try this next problem and then go ahead and play and see if you get it correct. So the next example is find the area of the region bound by the graph 2 minus x squared. So we're going to be up at 2, and then it's going to be an upside down parabola. And you can use your graphing calculator. Please make sure you've downloaded the graphing calculator if you don't have your own at home. Okay, so here's our parabola, and then we're looking at the line, just y equals x. So your basic line that has a slope of 1. Okay, so the area that we are trying to figure out is this yellow shaded region right here. So let's go ahead and set up our integral. We have the integral. Now we have to look at where do these functions intersect. And when we have a nice clean graph, we can just look and we use the x values. So at x equals -2 to x equals 1 is where this region is defined by. And then we are going to take, the parabola is the function on top, so 2 minus x squared, and then subtract the function below, the lower function, so that's just x. So then again, maybe do some cleanup. And we have negative x squared minus x plus 2 dx. Now, I am going to actually stop here, and you could continue on and find the integral. Maybe we'll find the integral and then I'll backtrack just as more review. Power rule, so negative 1/3 x cubed minus 1/2 x squared plus 2x. And we are integrating from -2 to 1. Okay, but you need to make yourself a note and you need to get on your graphing calculator, because from here on out, we're going to be doing a ton of definite integrals, and it is not realistic to sit there and do everything by hand because we're past kind of that key idea. So on the calculator, once you get kind of your function cleaned up, so you don't necessarily want to enter this first step right here. Once you get it cleaned up, let's go into our y equals, and you can go ahead and enter this function right here. So enter into your y equals negative x squared minus x plus 2, and then press graph. Okay, and then from there, what I'd like you to do is, if you recall, you can use the calculate button, and then you go to, so it's second calculate, and then go to option number 7, which is the integral. What am I doing here? Option number 7, which is the integral. Okay, and so then when you press enter, it says lower limit, and you need to go ahead and enter in your lower limit, which is -2. Press enter. Then it says upper limit at the bottom of your screen, and what is our upper limit? It's 1, and press enter. And then guess what it's going to give you? It's going to go ahead and give you the final answer of 4.5, which is the same thing as 9/2. Okay, so please don't just say, I'm going to not do it this way, because there are going to be some integrals that we cannot spend time just kind of obsessing over to try to figure out how to do it by hand. We've got to be able to use our calculator effectively from here on out. Okay, and that's our answer. The area under the curve is 9/2 units squared. 2 more problems. Okay, now example 3, our favorite trigonometry, yay. Okay, we can envision that if we're graphing y equals sine x and y equals cosine x, they're going to intersect infinitely many times. But periodic functions have kind of symmetry and repetition, so every region is going to have equal area. So they just want us to find one of those regions. So we are going to go ahead and, think about graphing sine. So let's first look at y equals the sine of x. So when I'm graphing that, okay, I'm thinking about what is the sine at 0. The sine at 0 is 0. And I'm going to go ahead and make my 1 here, and I'm going to make my -1 here to kind of spread it out a little bit. So then at pi over 2, the sine is 1, and then at pi it's 0. At 3 pi over 2, it's -1. So then we can see kind of that S shape take place for the parent graph of sine. Okay, then now let's go ahead and look at y equals cosine of x. So for y equals cosine of x, we're going to start at 1 for 0, and then at pi over 2, we're at 0. At pi, we're at -1. 3 pi over 2, we're at 0, and then at 2 pi, we're at 1. So now we can go ahead and connect those dots. Okay, that's going to be my graph there. Not perfect. And we can see that our goal is to find the area of this shaded region. Now, because my graph isn't perfect, we need to think about 2 things. What is our rectangle defined by? What is our related rectangle looking like? So if we think about drawing a rectangle, okay, the top of that rectangle is going to be defined by which function? Okay, the top is going to be defined by sine in this case. Okay, and then the bottom is going to be defined by cosine of whatever we want to input in our interval if we are taking the rectangle approach. So right away, we can think about, okay, the integral from, we don't know yet. We'll talk about that here in a second. But in order to find the height of the rectangle, what would we have to do? We would have to take the sine of x and subtract the cosine of x. That's very important that the order of those two is established. Okay, but now we need to know, okay, basically what is this point and what is this point where the graphs intersect. So going back to algebraic systems of equations, we're thinking about when is the cosine of x equal to the sine of x? So now we need to really think about our unit circle, and we know that sine and cosine are equivalent for the increments of pi over 4. But specifically, if the sine and cosine are identical, where does that happen? In quadrants 1 and 3. So in quadrant 1, okay, the angle would be pi over 4, and then in quadrant 3, it would be 5 pi over 4. So look back at that unit circle that's in the front of your textbook. So why was this important? Because they didn't come right out, and if we didn't have an accurate graph, we would have to do this scratch work to figure out those intervals, okay? So now from here, we can go ahead and look at the integral. Let's review integrals of sine and cosine. So integrating sine, we're thinking about, okay, negative cosine of x would give us positive sine x if I went ahead and found the derivative. So the integral of sine is negative cosine. And then the integral of negative cosine is going to be negative sine, sorry. And we are going from 5 pi over 4, pi over 4 to 5 pi over 4. All right. So at this point, then we would have to figure out, okay, what is the cosine of 5 pi over 4 and the sine of 5 pi over 4, and then same thing with just pi over 4. So now we're going to evaluate the definite integral. So the negative, I'm going to put this first part in brackets. What is the cosine of 5 pi over 4? Well, it's negative root 2 over 2, but we have to tack a negative in front of that. So root 2 over 2, okay, is the negative cosine. And then minus, what is the sine of 5 pi over 4? It's a negative root 2 over 2. So there's that double negative occurring again. And then now I'm going to evaluate for pi over 4. So what's the cosine of pi over 4? It's root 2 over 2, but we have a negative out front. So negative root 2 over 2 minus what's the sine of pi over 4? It's root 2 over 2. We are almost there. So now we have to work our algebra. So we have root 2 over 2 plus root 2 over 2, which is root 2. And then minus negative root 2 over 2 minus root 2 over 2 is negative root 2. So at this point, the double negative makes a positive. So what is the area under the curve? 2 root 2. Now, why did I not use the graphing calculator for this example? Because this is an exact answer, and if you use your graphing calculator, what's it going to give you? It is going to give you the approximations, okay? So I'll try to be specific when you need to give me exact, but a good rule of thumb is if it's kind of basic functions that you know you're expected to know sine and cosine of, make sure you do apply your knowledge of the unit circle. All right, final example. Okay, it says find the area of the region when we have the graph f of x, and then we have the graph of g of x. Okay, and it says, note that these curves intersect at more than 2 points. And you can see that. So if I use my color coding, okay, we have the green function is the parabola. So this right here is my g of x. And then if I get my yellow marker back out, this curve right here is my f of x. So we have to make two separate integrals because we need to find the area of this region right here. and then add it to the area of this region. You can't do this in one step. So if I treat kind of this portion as integral 1, I'm going to look at the integral from, look at your x values of the intersection points, -2 to 0. And what is my upper function? It's the f of x. You can see it in yellow. So I have 3, we have 3x cubed. For some reason, I can't make 3's right now. 3x cubed minus x squared minus 10x. And then we have to subtract the green function, which is -x squared plus 2x dx. But that's not going to give us the answer because we said we have to add, okay, another integral, which is just treated like a brand new problem. So from 0 to 2, what is our upper function? It's green, so -x squared plus 2x, and then subtract the yellow function, which is 3x cubed minus x squared minus 10x, and then we have a dx. So that got long, okay, but it's going to simplify quite nicely. So then if we do a little bit of simplification, we have -2 to 0. We have just 3x cubed, and then we combine -x squared, distribute your negative, so positive x squared, so the x squareds cancel out. And then we have -10x, but then we have -2x, so that gives us -12x. Don't make silly arithmetic errors. And then we're going to add that to the integral from 0 to 2 of, we have, let's see, -3x cubed. And then we have -x squared and a double -x squared, so those cancel out. And then we have 2x and then really plus 10x, so we have positive 12x dx. Okay, so now let's practice using our calculator one more time. So you need to just first focus on this integral. So go to your y equals, type in 3x cubed minus 12x, press enter, go to your graph, then go to calculate option number 7, and then track or find the integral from -2 is your lower, 0 is your upper, and when you press enter, that will give you 12. But that is not your answer because now we have to do the same thing, and you can probably guess it looks like these regions are symmetric, so we're going to talk about strategies here in the next few days. So it's probably going to also be 12, but just in case, go back into your y equals. You can do -3x cubed plus 12x, graph it, calculate the integral. 0 and 2 are your upper and lower bounds, and you get 12. So what is the area of the region from the that is shaded? It's 24 units squared. So we are going to leave it at that today. Please make sure you do the practice problems. I'm going to be pickier about you guys getting those done. More picky, I should say, than I was when you guys were in class, because it's very important that you get some practice since we're not face-to-face. And so make sure you do those problems, get them uploaded so that you can get points to add to your grade, and we will keep going with this idea on lesson number 2. Have a good one.